Hello, this is section 2.7, related rates in Calc AB. And these are pretty nice word problems that generally you're going to pick a formula that fits the scenario and the information that you're given. And you're going to be doing the derivative with respect to time. So this is actually implicit differentiation you're going to be doing. Just instead of doing the derivative with respect to x, you're going to do the derivative with respect to time. So one really good example is if you were to drop a rock into a pond, it's going to create a ripple, and the shape of that ripple is a circle. Well, as that circle gets bigger over time, the radius is changing, the circumference, the area, all of those are changing, not at the same rate, but the rates are related. So that's kind of the idea. We also talked about a balloon, blowing up a balloon, like a spherical balloon. Well, again, your radius is changing as you're blowing it up. Your volume, your surface area, all of those are changing at different rates, but they're all related in terms of time. So I'm going to come back and look at this box after we do an example. So let's talk about this first one. So a 25-foot ladder is leaning against a house. Base of the ladder is pulled away from the house at a rate of 2 feet per second. How fast is the top of the ladder moving down the wall when the base is 7 feet from the house? So your first task is to figure out a formula that fits your scenario. And right triangles, you've got the area of a right triangle, you've got your SOHCAHTOA formulas with your angles, you've got Pythagorean Theorem, so you have lots of formulas to pick from. So, but you just have to ask yourself, this is dealing with the side lengths of your right triangle, so that's why we picked Pythagorean Theorem. Okay. Now, when you have your formula, I like to actually plug, if there's ever a variable that's not changing, so as that ladder is being pulled out, the top is coming down. Well, the ladder length doesn't change, so you could plug 25 in before you do the derivative. Or you can do the derivative and I'll show you, you're going to realize that you could have plugged it in. But I think we're ready. We're ready to do the derivative. We're using all the side lengths of our right triangle. So now here's where you use implicit differentiation. So you do the derivative of x squared, that's 2x times dx dt, plus and then 2y times dy dt, and then here's your 2c, c is the ladder length, times dc dt. Now you go into plugging in the information that you're given. So 2 times 7, that's the moment in time that we're pausing. We're saying, okay, when the base is 7 feet, how fast is that ladder moving down the wall? And you can see as you start to pull that base away, at the beginning, it's going to move pretty slow. But as that base gets farther out, it's going to eventually get down to almost to where it'll slam down at the very end. So it's going to get faster as that base gets pulled out. And we're pausing and saying, how fast is it moving at this particular moment when the base is 7 feet away? Okay, so that's why we put 7 in for x, and then the dx dt represents your rate. And they told us that. It's 2 feet per second. Because that length is getting bigger, that's why it's a positive rate. So be careful with that. Plus 2 times, now we had to figure out 24 because that moment in time we're pausing is when the base is 7. We know the hypotenuse is 25, so we'll have to figure out the y length. So that's my work here. I'm figuring out y when the base is 7, excuse me. So that's where that's coming from. dy dt is what we're trying to figure out. How fast is it moving down the wall? And then equals. Now here's where you realize, oh, I could have put the number in because 2 times the ladder length, but then dc dt, the ladder's not changing. So you actually plug 0 in. And here's where you realized, oh, I could have put 25 here because the derivative of a number is just 0. But so then when you solve this all out for dy dt, you get this lovely decimal. We always round 3 decimal places, and you always write your answer in a complete sentence with units. And make sure you make it relevant to the problem. Say what's going on. Don't say it. Say the ladder is moving down the wall, and you can put the rate, always rounding 3 decimal places, and then the units. And if you want to be even more specific, you could also say when the base is 7 feet. That kind of gives that time element to it. Okay, so noun, unit, and then time would be the best sentence. Okay, so now if we come back up here, so here's the guidelines. So to identify all given quantities to be determined, make a sketch, label the quantities. I don't write the quantities and label them, but if that's something you think would be helpful, go for it. Write an equation involving the variables whose rates of change either are given or to be determined. So that's where we determined we're working with the side lengths, so it makes sense to use Pythagorean theorem. Use the chain rule, implicitly differentiate both sides with respect to time. That's what we did here. After completing step 3, substitute. Here's where you substitute and you hope that you only have one variable left and it's the variable you're trying to solve for. So that's what we did in this step. And then after that, you got your answers. So when using these guys, be sure to perform step 3 before step 4. So yes, this is very important. Make sure you do not put any numbers in for any variables unless they're not changing. So notice we kept the x and the y. Those are changing. So never put numbers into a variable before you do the derivative unless it's something that's not changing. All right, let's look at another one. So a sand and gravel plant, added sand and gravel plant. Sand is falling off a conveyor and into a conical pile at the rate of 10 cubic feet per minute. So we're pouring sand and it's forming this cone here. The diameter of the base of the cone is approximately 3 times the altitude. At what rate is the height of the pile changing when the pile is 15 feet high? So that's that moment in time. When that pile is 15 feet high, how fast is it changing? How fast is at what rate is the height of the pile changing when the pile is 15 feet high? Okay, so first and foremost, you have to pick the formula. Do we want surface area of the cone? In this case, you're dealing with, notice your rate is 10 cubic feet per minute. That's volume. So pick the volume formula. That's going to be your eventual dV dt. So here's the volume formula for a cone. Now you ask yourself, I do not like when I see 3 variables. Is there a variable that we can either replace with a number or maybe make it in terms of another variable? And in this case, all 3 of these are changing. As that sand's being poured in, the height, the radius, and the volume are all changing. But they gave you a really helpful part. It says the diameter of the base of the cone is approximately 3 times the altitude. So notice I came over here. Diameter is 3 times the altitude. Diameter is 2 times r, and I was able to solve for r and plug this in. Notice before I've done my derivative. And I want it in terms of h because that's what it's asking. At what rate is the height changing? So I don't want to make this in terms of r. I don't care about the radius changing. So now I've got a new formula that's now only 2 variables. Perfect. So now we're ready to do the derivative with respect to time. So v turns into dv dt. This is a scalar. And then do this derivative, 3h squared times dh dt. We need the dh dt, that's what we're trying to find, so plug all your information in, and that's where I'm getting this answer up here. So the height is increasing 0.006 feet per minute. Okay. All right, let's look at another one. So here's a balloon problem. Air is being pumped into a spherical balloon at a rate of 4.5 cubic inches per minute. That's a good hint that you're probably going to use the volume formula. Find the rate at which the radius of the balloon, change of the radius when the radius is 2. So when that radius is 2 inches, that's when we're pausing the moment in time and seeing how fast the radius is changing. Okay. Excuse me. So here's the volume formula for a sphere. Do I need to keep the variables? V and R. Yes, they're both changing. I only have 2 variables, so I'm okay with that. And then you're ready to do the derivative. So here's my dv dt. 4/3 pi is a scalar. So then I did the derivative of 3r. So this is 3r squared times dr dt. I need the dr dt. That's what we're solving for. So I plug the variables in. Volume's increasing 4.5. That's your dv dt. You've got this stuff. And then we're pausing when the radius is 2. And then you solve. Okay. Pretty straightforward. Always round 3 decimal places and always put units, and make sure you address. This is not good. The radius is increasing. I should have made the noun. I should have said the balloon's radius is increasing. Okay, so that's not good. Make sure you put a noun in there. All right. Now, this is an interesting problem. This is a fun one. So a square baseball diamond has sides that are 90 feet long. A player 26 feet from third base is running at a speed of 30 feet per second. At what rate is the player's distance from home plate changing? All right, so can you see the runner over here going from second to third? And you can see that right triangle that I made bigger right here, so you can see it a little bit better. Then it's changing. Okay. All right, so we're trying to figure out how fast this rate, the distance from the runner to home, is changing. So that's the C right here. We're trying to find dc dt. So we're going to use Pythagorean Theorem. This 90, that's not going to change. That stays, that's a number we can plug in because that's not changing. You can only do that if the variable is not changing. Now your B, that's this distance, that's of course changing. That's getting smaller. So that rate should be negative. And then the C is here, and that's your rate at which the distance from the home plate. Okay. So once you've done that, now you're ready to do the derivative. So 90 squared is a number, that's just 0. And here we used our implicit, so that's 2b times db dt equals 2c times dc dt. So now that we've got our derivative, now you need to go in, you're in plug-in mode. So 2 times b, what is that distance? That's here. And it tells you a player is 26 feet from third base. So that's nice. Be careful there. What if they had said that runner has run this distance, and you would have had to subtract from 90, so just watch out for that. But they told you 26. And then here, when you go to plug in 20, it says it's running at a speed of 30 feet per second, but you have to be careful because B, that's this distance, is getting smaller. So that's why we're putting in a negative rate when we put in 30. So just be careful with that. Equals 2 times, and then we had to solve for C. So at that particular moment, when this distance is 26, this distance is 90, we had to use Pythagorean Theorem real fast to figure out what C is at that particular moment. And it's this lovely square root of 8,776. And then dc dt is what we're trying to figure out. So of course, divide, you get this lovely answer here. So I said the distance from home is decreasing 8.326 feet per second. And you could say when the player is 26 feet away from third base, if you want to be even more detailed. Okay, then this last question real fast. So when is the water drained out of a conical tank? Volume, radius, height of the water. Well, these values are related by the equation. They gave you the equation. Differentiate the above equation implicitly with respect to time. So we haven't been asked to do anything yet. They just want you to do the derivative. So I like it because it has you do the product rule, and you're keeping all 3 variables. So dv dt, and then first times derivative of the second plus second times derivative of the first. So look through that and see if that makes sense. Now down here at the bottom, from this equation, you can see that the rate of change of V is related to the rates of change of H and R. Suppose that the height is changing. So I believe they give you everything you need to just plug and chug for that. Okay. Now, we'll talk a little bit more. These are interesting problems because you can end up, you might needing a proportion. I think there's one in your homework where you end up having to do this, so we'll talk about that in class, but try that problem in your homework. Don't skip it. Try it and work through these. You'll start to see patterns with these types of problems, and it really comes down to picking the correct formula, making sure you don't put any numbers in for variables that are changing before you do the derivative. Do the derivative first, then plug the numbers in, unless it's something that's not changing. Okay, so keep practicing. Always round 3 decimal places. Write your answer in a complete sentence with units. Okay, thanks.